Hello, welcome to the final lesson in our free module from the Networking Fundamentals course. This lesson is the summary lesson to everything we have learned so far. The purpose of this series was to teach you the very core of networking, how data flows through a network. In this series, we talked through the OSI model and the different functions each layer is responsible for. We talked through how hosts on the same network communicate with each other, regardless of how they are connected. We talked through switches and how they facilitate communication within a network. We also talked through how hosts on foreign networks speak with each other, whether they are connected behind one router, or multiple routers, or on opposite sides of the internet. We discussed what routers do, and how they learn routes and hand data off to one another. We covered each of these things in detail in prior videos in this module. And in this lesson, we're going to tie elements from each of those videos together into a comprehensive summary lesson. At its core, understanding how data flows through a network comes down to understanding three specific tables: a MAC address table, an ARP table, also referred to as an ARP cache, and a routing table. Each of these tables is a mapping of something to something else. A MAC address table is a mapping of a switch port to a MAC address, and an ARP table is a mapping of an IP address to a MAC address, and a routing table is a mapping of an IP network to an interface, or an IP network to an IP address of the next router in the path, also known as the next hop IP address. These three tables are crucial to moving data through a network, and we're going to show you everything that happens with these three tables as data is flowing through this network topology. This topology has three routers, routers 1, 2, and 3, and three hosts, hosts A, B, and C. Each host exists within a network, and all the devices have IP addresses in the respective network. And finally, each of these wires are connected to NICs, and each of those NICs have unique MAC addresses. And again, I'm only showing you the first 4 digits of MAC addresses to keep things simple. Now, in the case of the switch, since we are only sending traffic through the switch and not to or from the switch's MAC address and or IP addresses are irrelevant. We elaborated on this point back in lesson 4. So for our switch, we only need a label for the two switch ports that these wires are connected to. In this case, they're going to be port 4 and port 5. Each of the devices in this topology are going to use one or more of these tables to process data, and we're going to show them to you in these gray boxes. Our switch is only going to have a MAC address table, and you're going to see the entries of the MAC address table right there. Our routers have both an ARP table and a routing table. And our hosts, being very similar to routers as we discussed back in lesson 5, also have both an ARP table and a routing table. Now both the MAC address table and the ARP tables are going to be populated dynamically as traffic is flowing through this network. The routing table, however, must be populated ahead of time. Recall that back in lesson 5, we said that if a router receives a packet with a destination IP address not in the routing table, that packet would be dropped. So at this point, if our host started sending packets, since our routers have empty routing tables, everything would just be dropped. Therefore, the routing tables must be populated before any data can be sent through this topology. So let's fill in all the entries for all the routing tables in this topology, starting with host A's routing table. Host A only needs a default gateway, also known as a default route. The default route will be represented as a route for the 0.0.0.0/0 network, which includes all IPv4 addresses. This route is pointing to the IP address of this interface of router 1, 11.8.8.1. This will tell host A to use router 1 anytime it's trying to speak to anything on a foreign network. Host B will also have a default gateway pointing to this interface IP address on R2, 22.7.7.1, and host C will also have a default gateway pointing to this interface IP address on router 3, the IP address 33.6.6.1. Each of our routers will have two routes. First, they will have a directly connected route for the networks that they are attached to. Notice R1 has a directly connected route for the 11.8.8.0/24 network. Then each of the routers are going to have a default route pointing to the internet. Now normally, that default route would point to a specific router IP address somewhere on the internet. But to keep things simple, we'll simply abstract that away and say that this route is pointing simply to the internet. And now we are ready for host A to send some data. I want to show you the details of this data, but there isn't enough room here to show you the source and destination information. Instead, I'll show you this data in more detail in this box right here. Inside this data payload is just a bunch of ones and zeros. The network doesn't know or doesn't care what specifically those ones and zeros are doing. It's just arbitrary computer code that needs to be sent to another host. Host A will start by adding a layer 3 header to this data. This will facilitate the end-to-end delivery of this data. To begin, host A will be sending this packet to host B. So the source IP address of this packet is going to be the IP address of host A, 11.8.8.11. And the destination IP address of this packet is going to be the IP address of host B, 22.7.7.22. And now we are at the starting point of our illustration, and we are ready to follow this packet as it travels through this topology. The first thing that happens when host A is trying to send this data is host A will compare the destination IP address of the packet with its own IP address and subnet mask to determine that the destination IP address is on a foreign network. Therefore, this packet must be sent to host A's default gateway, which is router 1. But at this point, host A's ARP table is empty, which means host A doesn't know router 1's MAC address, and therefore is unable to put together the necessary layer 2 header, which will take this packet across this hop. So host A will hang on to this packet and first go through the ARP process to resolve router 1's MAC address. The ARP request is also going to have a layer 2 header. That layer 2 header is going to have a source MAC address of host A and a destination MAC address of all Fs. That's the broadcast MAC address. This will tell the network that this ARP request should be sent to everybody in this network. When host A puts that on the wire, it'll arrive on our switch. Anytime something's received on a switch, it's going to try and learn the mapping between the receiving switch port and the source MAC address. In this case, the source MAC address of this frame is A1A1, and the receiving switch port is port 4. Therefore, our switch is going to learn that something out port 4 owns the MAC address A1A1. Then, the switch is going to look at the destination MAC address. In this case, the destination MAC address is all Fs, which tells the switch that no matter what, it's going to do the flooding action to send this frame out all ports. Now in our topology, there's only 2 devices in this network. But if there were other devices plugged to this switch, they would also receive a copy of this frame. But for us, that frame would only be sent out port 5, where it'll arrive on router 1. Upon arriving to router 1 will get to learn the ARP mapping of the sender. Recall that when we discussed ARP, we told you that inside the ARP request is the ARP mapping of the sender. So by simply receiving the ARP request, router 1 is able to learn that a device with the IP address 11.8.8.11 maps to the MAC address A1A1. Then router 1 will generate an ARP response. This ARP response is going to look like this. It's going to have a source MAC address of router 1's NIC and a destination MAC address of host A. This is a unicast ARP response meant to be delivered directly back to host A. Router 1 will put that on the wire, where it'll arrive on our switch. And again, just like before, since the switch received something on port 5, it's able to learn that a device out port 5 owns the MAC address EEE1. Then the switch will again take a look at the destination MAC address. In this case, the destination MAC address is A1A1, and our switch already knows that that MAC address exists out port 4, and will therefore forward this frame out port 4, where it'll finally arrive back to host A. Once host A receives it, host A will learn the MAC address that it was trying to resolve. In this case, that the IP address 11.8.8.1 maps to the MAC address EEE1. And now, host A has the necessary information to complete this layer 2 header, which will take our data packet to the router. That layer 2 header will have a source MAC address of host A and a destination MAC address of the router, now that host A knows the router's MAC address. This layer 2 header will handle delivering this packet across its first hop, which in fact is the goal of layer 2, hop-to-hop delivery. Now if that idea isn't familiar to you, we unpacked it when we discussed the OSI model back in lesson 2. Either way, host A will put all of this onto the wire, where it'll arrive onto the switch. Once it gets to the switch will again try and learn what it can from this incoming frame. This frame arrived on port 4 and had a source MAC address of A1A1, and our switch already has that entry in its MAC address table. So there's nothing new for the switch to learn, but this particular entry will be refreshed in the switch's MAC address table. Then again, the switch is going to look at the destination MAC address to determine that this frame should be forwarded out port 5, where it'll put it on the wire and send it out towards router 1. Once that arrives to router 1 will strip the layer 2 header. The purpose of that header was again to take the packet from host A to router 1. It did that successfully and we no longer need it. Then router 1 will take a look at its routing table to determine where it's going to send this packet next. The destination IP address of this packet is the IP address 22.7.7.22, which matches this route for router 1, which means router 1 knows that this packet is going to be sent across the internet. As we discussed earlier in this module, the internet is really just a bunch of other routers that'll hand data off to one another. And normally, this route would point specifically to one of these routers. But we unpacked the details of how routers hand data to other routers back in lesson 5. So rather than repeat myself, I'll simply direct you to that video if you want more information on this process. I'll also mention that there are actually many more ways that this packet can get through the internet to router 2. All of those ways are contained in what's known as WAN technologies, and the details of each of them are outside the scope of this module. One way or another, this packet will be passed from router to router across the internet until it finally gets to router 2. And when it gets to router 2 is going to take a look at its routing table to try and figure out how to deliver this packet. The destination IP address of this packet hasn't changed, which means this packet matches this route, and router 2 knows it's going to be delivering this packet to its final hop within the directly connected network that router 2 is attached to. However, at this point, router 2's ARP table is empty, which means router 2 is unable to put together the layer 2 header necessary to take this packet to host B. So just like before, router 2 is going to have to put that packet on hold and send out an ARP request. The ARP request will be sent to the broadcast MAC address, but this time the source MAC address is going to be router 2's MAC address. This packet will be put onto the wire where it will arrive on host B. Upon receiving the ARP request, host B gets to learn the ARP mapping of the sender of that ARP request. In this case, the IP address 22.7.7.1 maps to the MAC address EEE2. Then host B will generate a response. That ARP response will look like this. It's going to be a unicast frame sent with a source MAC address of B2B2 and a destination MAC address of EEE2. That ARP response will be put onto the wire where it will arrive on router 2, and router 2 will learn the ARP mapping that it was trying to learn, that the IP address 22.7.7.22 maps to the MAC address B2B2. And now router 2 has all the information necessary to put together the layer 2 header that'll take this packet to host B. That layer 2 header is going to have a source MAC address of router 2 and a destination MAC address of host B. Router 2 can now put the packet on the wire where it'll finally arrive on host B. Now, normally you wouldn't see a host plugged directly into a router. Normally, this host would be connected to a switch, which would then possibly be connected to other switches, which would then finally connect to the router. But we've already illustrated a switch's operation back here, and we discussed how frames travel through multiple switches back in lesson 4. So to keep things simple, this network does not have any switches. But if you want to understand how data flows through multiple switches, check out lesson 4. Either way, once this packet arrives on host B, the first thing host B does is strip the layer 2 header. Again, that header only existed to take this packet from router 2 to host B. The next thing host B does is strip the layer 3 header. Again, the purpose of that header was to handle the end-to-end delivery of this data, which it did so successfully. And now host B can finally process all those ones and zeros contained within that data payload. Once it's processed that data, it can now generate a response. And that response, just like before, is simply a data payload which includes a bunch of ones and zeros. And now we'll step through all the steps required to get this data payload back through the network to host A. Now, what you'll see is that this is going to go much quicker than before, because most of our tables have already been populated. Host B will start by throwing a layer 3 header onto that data. That layer 3 header is going to have a source IP address of host B and a destination IP address of host A. In this case, since this packet is going to something on a foreign network, we know that it must be sent to router 2's IP address. And at this point, host B already has the ARP mapping for router 2's IP address and can therefore already put together the layer 2 header necessary to get this packet across its first hop. This is what will allow this packet to make it across this hop. Upon arriving on router 2 will strip the layer 2 header, and then router 2 will take a look at its routing table to figure out where this packet should go next. In this case, the destination IP address 11.8.8.11 only matches the default route, so router 2 knows that this is going to be sent out towards the internet. And again, we've abstracted that process out, so it'll be handed from router to router across the internet, where it'll finally arrive on router 1. Upon arriving on router 1 will take a look at its routing table and determine that the destination IP address matches the directly connected route, so router 1 knows that this destination IP address is the final hop for this particular packet. And router 1 also happens to already know the MAC address for that particular IP address. So router 1 has all the necessary information to put together a layer 2 header that'll take this packet across its final hop. That layer 2 header is going to have a source MAC address of router 1 and a destination MAC address of host A. Router 1 can then put that packet onto the wire. It'll arrive on our switch, and just like before, our switch is going to try to learn. It'll try and map the receiving switch port, which is 5, to the source MAC address of the incoming frame, EEE1, and it'll notice that it already has that entry in its MAC address table. So there's nothing new to learn, so this entry will simply be refreshed in the switch's MAC address table. Then the switch will look at the destination MAC address A1A1, and the switch knows how to deliver a frame to the destination MAC address A1A1. This frame will be sent out port 4. It'll then finally arrive back on host A. Host A will strip the layer 2 header. Again, that header took the packet from this NIC to this NIC. Host A will then strip the layer 3 header, which took the data from this end to this end. And finally, host A will process that response data. So we just showed you everything that happens to get data from host A all the way to host B and back again. And we showed you how each of the devices involved in this process used a MAC address table, an ARP table, and a routing table to make that happen. Next, host A is going to send some data to host C. Now, if you feel that this is beginning to get repetitive, awesome. That's great. That's exactly right, and it means you're learning how it all works. Remember, all these devices, hosts, switches, routers, all follow simple, consistent packet processing rules. If you understand those rules, you can scale this topology to hundreds of devices and still walk your way through each step necessary. For this last packet, going from host A to host C, I want you to test yourself. Try to guess what happens next at each step just before I explain it. With that in mind, the first thing that host A does to send this data to host C is throw a layer 3 header onto that data. That layer 3 header is going to have a source IP address of host A and a destination IP address of host C. Then, since host A knows this packet is going to a foreign network, host A is going to look at its default route to determine the default gateway's IP address, which is router 1. And since host A already has the ARP mapping for its default gateway's IP address, it can already put together the layer 2 header, which will take this packet to router 1. That layer 2 header is going to have a source MAC address of host A and a destination MAC address of router 1. Host A will put this onto the wire, where it'll arrive on the switch. The switch will try and update its MAC address table with an entry for port 4, mapping to the source MAC address A1A1. Since that entry already exists, that entry is simply going to be refreshed in the MAC address table. Then the switch is going to look at the destination MAC address to determine where to send this packet next. That MAC address exists out port 5, which will have this switch send this frame out port 5. It'll then arrive on the router, and the router is going to strip the layer 2 header. And now router 1 is going to look at its routing table to determine where to send this packet next. The destination IP address on this packet matches the default route, which means router 1 is going to send this packet across the internet, where it'll finally arrive on router 3. When router 3 gets it, router 3 is going to again look at the destination IP address and determine that it matches the directly connected route in router 3's routing table. This tells router 3 that it's going to have to put a layer 2 header onto this packet that matches the MAC address associated with this IP address right here. But at this point, router 3 does not have anything in its ARP table, so it cannot put together the appropriate layer 2 header. Therefore, just like before, router 3 is going to put that packet on hold, and then router 3 is going to send out an ARP request. That ARP request will be sent to the broadcast MAC address, which will ensure that this ARP request gets delivered to everybody on this particular network, which means host C will definitely receive that ARP request. Upon receiving the ARP request, host C will learn the ARP mapping of the sender of that ARP request, which in this case is the IP address 33.6.6.1 and the MAC address EEE3. Then host C will put together the ARP response. That ARP response will look like this. The ARP response is sent as a unicast frame, meaning it's going from a specific MAC address to another specific MAC address. This will get the ARP response back to router 3, and then router 3 will finally learn the ARP mapping it was trying to learn. And now, router 3 has everything it needs to put together the appropriate layer 2 header, which will take this packet across its final hop to host C. Router 3 will put that onto the wire, where it'll arrive on host C. Host C will strip the layer 2 header. Host C will strip the layer 3 header, and host C will finally process the data. And as with most internet communication, when you send something, you generally expect a response, so host C is now going to send that response back to host A. Host C will throw a layer 3 header onto that packet. That layer 3 header is going to have a source IP address of host C and a destination IP address of host A. Host C knows it's trying to speak to something on a foreign network, so host C knows that this must be sent to the default gateway, in this case router 3. And host C happens to already have the ARP mapping for the default gateway, so it has all the information it needs to put together this layer 2 header, which includes the destination MAC address of router 3. Host C will put that onto the wire, where it'll arrive on router 3. Router 3 will strip the layer 2 header, and then router 3 will take a look at its routing table to determine where to send this packet. The destination IP address of this packet matches the default route, so router 3 will send that packet out towards the internet, where it'll finally arrive on router 1. Router 1 will take a look at its routing table and compare the destination IP address to see which route matches. In this case, this destination IP address matches our directly connected route, which means router 1 knows that this packet will be delivered to its final hop. And router 1 happens to already know the ARP mapping for this particular destination IP address. So router 1 has all the necessary information to put together a layer 2 header with a source MAC address of router 1 and a destination MAC address of host A. That will get sent onto the wire, where it'll arrive on the switch. And again, the switch has nothing new to learn, so it'll simply refresh that entry in its MAC address table. Then the switch will look at the destination MAC address to determine that this frame should be sent out port 4. The switch will put that onto the wire, where it'll arrive on host A. Host A will then strip the layer 2 header. Host A will then strip the layer 3 header. And finally, host A will process the response from host C. And that, my friends, is every single step that is necessary to get a packet from host A to host B and back, and host A to host C and back. And that is how these 3 tables were used to facilitate that entire process. The last idea I want to leave you with has to do with a very common interview questions for networking engineering type roles. That interview question looks something like this. Tell me everything that happens when you type www.google.com into a web browser. This question is trying to see if you can apply what we learned in this video to the simple act of visiting a website. Browsing to a website essentially involves 2 phases. First, using DNS to resolve a domain name into an IP address. And second, sending an HTTP request to that IP address. Well, in our illustration, the first thing we did was send a packet from host A to host B. But what if this packet was actually a DNS request? And what if host B was actually a DNS server? The response from the DNS server would have given us the IP address of the web server for the domain you're trying to visit. Well, what if that web server was actually host C? then that packet that we sent from host A to host C would have actually been an HTTP request. So you see, everything we did in this video was in service of answering this very common interview question. And now you can confidently answer this question when you inevitably come across it. But it's more than just an interview question though. It's a fundamental part of understanding how internet connectivity works. Next time your friend or coworker or customer or parent asks you why they can't access their email or their favorite website, you'll know exactly what should have occurred if everything was working, and you'll be better equipped to troubleshoot and identify exactly where the failure might be. And with that said, we bring this lesson and this entire module to a close. If you followed each of the lessons in this module, then congratulations. You can now say you understand how data moves through the internet. If you're looking to become a network engineer, there is no better start to that journey than this video series. And if you're in any other IT or tech role, then now you have a better idea of what it is those networking folks do all day. And this type of cross-discipline training will pay off exponentially as you can now interact with your networking team much more efficiently. I truly hope you have gotten a lot out of this series. If you have, I'd love to hear about it. What was your favorite? I want to teach you something about networking and network protocols. And the best way to do this is to show you a quick little demonstration. At the surface, this will teach you the difference between HTML and HTTP. But beneath that, you'll also learn how internet. For this demonstration, we're going to use two web browsers. I'm going to use Firefox, but you could probably replicate this in any other web browser. I'm going to start by going to a web page. The web page is pracnet.net. www.simple.html. Once I hit enter, that web page will load. And here you see a simple web page that, not to brag or anything, I wrote myself. Notice all the cool things that exist on this web page. It has a title, it has a subtitle, it has this line dividing these two sections. It's got some text that is decorated as bold, some text that is decorated as italic, and of course an image. But I want to show you the code that actually created this masterpiece. And to do that, I'm going to right click on the web page and go to View Page Source. This will show you the actual HTML. There's a lot of bad information out there about layers 5, 6, and 7 of the OSI model. In fact, there are many resources out there that describe the OSI model as merely something to memorize. I think that's a huge disservice. There's a way of understanding the OSI model from a practical perspective, as a series of components that all contribute towards making the internet work. That's the strategy I took when I published my 2 videos on the OSI model. Those videos focused on layers 1 through 4. The most common request I got in the comments of those videos was to continue with layers 5, 6, and 7. So here we are. The OSI model consists of 7 different layers that each have a specific responsibility which contribute to the overall goal of networking, which is to allow 2 users to use computers to share data between each other. If each layer is doing its responsibility successfully, then the goal of networking is attained, which means the internet works. There are many resources that unpack layers 1, 2, 3, and 4, but very few that really pick apart layers 5, 6, and 7. I call these the forgotten layers of the OSI model. Part of that is because the other popular networking models, the TCP/IP models, simply combine these layers as a single aggregated application layer. Now, there's good reason for that, and you'll understand those reasons towards the end of this video. But what I want to do in this video is unpack the details of layer 5, 6, and 7, and specifically how each of those layers contribute towards the goal of networking. Before we can understand these layers, however, we have to understand the layers beneath it. Specifically, you must understand the terms hop-to-hop, end-to-end, and service-to-service, and how each of those apply towards the goal of networking. If you're unfamiliar with those terms, then please check out my other 2 videos on the OSI model. I promise it'll be the best take on not only understanding the OSI model, but also how to explain it to others. With that said, let's get into the forgotten layers of the OSI model, starting with layer 5. To understand layer 5 of the OSI model, you have to understand that this model was created long before the days of personal computers, or PCs. Back in those days, computing was done on large, massive machines called mainframes, and these were often so big that they took up entire rooms. The computing resources on these enormous mainframes were then accessed by people using what is known as dumb terminals, which were effectively just a monitor and a keyboard plugged into these mainframes. No actual processing of data was done on these dumb terminals. All the actual computing was done on the mainframes. Fun fact, this was also the model that Linux was created in. This is why Linux is often described as a multi-user operating system. In any case, all the computing was done on these large mainframes, and users would connect to these mainframes using dumb terminals. And then, those mainframes were then connected to other mainframes, which also had their own set of users using their own set of dumb terminals. And here we can define the problem that layer 5 is meant to solve. Notice this blue user is using this mainframe to speak to this blue user using that mainframe. At the same time, these 2 green users are also speaking to each other using these 2 mainframes. Well, if both of those mainframes are doing all the computing and sending the data between each other, then the packets that are sent from this mainframe to the other are going to have the same layer 2 address, like a MAC address, the same layer 3 address, like an IP address, and even potentially the same layer 4 addresses, like ports. Which then begs the question, how is the data between these 2 blue users going to be kept separate from the data between these 2 green users? That's where layer 5 comes into play. Layer 5 is there to distinguish between user sessions. It allows networking protocols to identify a user independently from their layer 2, layer 3, or layer 4 addresses. Okay, so that makes sense, but is layer 5 simply an artifact of legacy computing on these mainframe computers? Well, no. You actually use something that I would categorize as a layer 5 component every day when you're browsing the web. Let me show you. Let's say these two blue users are not using mainframes to speak to each other. And instead, this user is actually a web server for the site site.com, and this user is simply someone using a mobile phone. This mobile phone is currently logged into a Wi-Fi network at this user's house, and this phone uses this connection to log into the site site.com. But what happens if this user then decides that they want to go to a coffee shop and connect to the Wi-Fi network there? Since this is a different network, they're going to have a new IP address, which means this information is going to change. And if the website is identifying this user with layer 1 through 4 information, then this user is going to have to log back into the website every time they connect to a new Wi-Fi network, because in each case, they're going to be getting a new IP address. Instead, since we're using HTTP to access this website, HTTP has a functionality known as HTTP cookies. These cookies are simply arbitrary text strings that store user-specific information that is created by the server. What happens is when the user logs into the website, the server generates one of these cookies and sends it to the user. This cookie then stays with the user. And if this user logs into a new Wi-Fi network with new layer 2 through 4 information, that user still has the same cookie. And the website can still identify this user independent from whatever layer 2, layer 3, and layer 4 addresses that user might maintain. So you see, HTTP cookies are a perfect example of layer 5's responsibilities in the OSI model. They allow the network to identify user independently from the layer 2, 3, and 4 addresses. Which then brings us to layer 6. To understand the presentation layer, we're going to simulate a packet arriving on the web server for site.com. Recall that every packet is really nothing more than a series of ones and zeros. And because of the rest of the layers of the OSI model, we know that this packet is successfully delivered to the web server, arrived to the right MAC address, arrived to the right IP address, arrived to the right port, and arrived to the right user session. Which now brings us to layer 6. What layer 6 does is it tells us how to interpret the ones and zeros. There are many ways to interpret those ones and zeros. For example, should we group those ones and zeros in sets of 6 bits as base 64 encoding would require? This would mean each combination of 6 bits would turn into a new base 64 character. Or should we interpret those ones and zeros in groups of 4 bits? This is what hexadecimal would require, where each group of 4 ones and zeros represents a new hexadecimal character. Or should we interpret those ones and zeros as long numbers or integers? If we were to interpret all these ones and zeros as 32-bit numbers, this number would be 1 billion and change, and this number would be 796 million and change. Alternatively, maybe we're interpreting this as a single large 64-bit number, in which case this string of 64 ones and zeros could be translated to this huge number in decimal. So you see, that's what layer 6 tells us. It tells us what do we do with these ones and zeros. Now, earlier we used HTTP as an example, and we can continue to do so. HTTP as a protocol uses extended ASCII encoding. Extended ASCII takes all the ones and zeros and groups them into sets of 8 bits and interprets each of those 8 bits as a different ASCII character. This combination of ones and zeros translates to the letter G, and this combination of ones and zeros translates to the letter E, and this combination translates to the letter T, and so on. And that's what layer 6 provides. It tells us what to do with the received ones and zeros that have been successfully processed through the OSI model and delivered to the right user session. Which then brings us to layer 7. If layer 6 told us how to interpret the ones and zeros that have been received, layer 7 will tell us what do we do with the interpreted characters. Or, said another way, layer 7 will actually define the application commands. These 3 bytes of ones and zeros turn into the letters G, E, and T. And the command get in HTTP is the command you would use to fetch a particular web page. What you're seeing here is actually the first 8 characters of an HTTP request asking for the page simple.html using HTTP 1.1 from the host pracnet.net. And if that looks familiar, that's because it's the exact HTTP request we made in my last video, where I showed you how to make an HTTP request using Telnet. And if you haven't seen that video, I think that one plus this video work well together to really explain how networking protocols work. Either way, that is what layer 7 of the OSI model does, and that actually concludes my description of what the forgotten layers of the OSI model actually do. But before I let you go, there's a few more ideas I have to leave you with. Throughout this lesson, we've been using HTTP as our example protocol. We told you that HTTP, to accomplish the goals of session management, uses HTTP cookies. And for layer 6, HTTP uses extended ASCII encoded. And for layer 7, HTTP has its own set of application commands. But there are other protocols that exist beyond just HTTP. For example, FTP. Well, it doesn't really make sense for FTP to use HTTP cookies to accomplish its layer 5 goals. FTP is in fact free to choose how to implement layer 5 in any way it deems necessary, or to not implement it at all. FTP in fact doesn't have a way to identify a user session independent from the layers below it. FTP uses layer 3 and layer 4 information to identify a user, which means if you are in the middle of an FTP session and your IP address changes, you're going to have to log back into that FTP server. For layer 6, FTP also uses extended ASCII encoding, and for layer 7, FTP has its own set of application commands. So that's just HTTP and FTP, two of the maybe thousands of protocols that exist. And you can see that each of those protocols can implement layers 5, 6, and 7 in whatever way that makes the most sense for that particular application. That is why the TCP/IP models combine those layers into a single aggregate application layer. Since every protocol and application is going to implement their own way of doing these three goals, it makes sense to combine those as a single application layer. So in the end, whether you're using the 7-layer OSI model, the 5-layer TCP/IP model, or even the somewhat legacy 4-layer TCP/IP model, one way or another, each of these are merely models. They are simply a way of understanding computer networking. Don't try too hard to fit everything you learn in the networking world into one of these layers or one of these models. That's not the goal. These are simply abstractions to teach you how computer networking can work. In the end, each of these models are there to teach you the concept of layers of abstraction. One layer has a responsibility, and that precludes the other layers from having to worry about that responsibility. Layer 3 can do its job of end-to-end delivery without having to worry about how the ones and zeros are going to be delivered across every router in the path. And HTTP cookies work the same whether you're using IPv4 or IPv6. Each layer's goals are abstracted from the other layers. Understanding the OSI model or the TCP/IP model in that way will set you up for success when you're learning deeper things in the networking world, like tunneling and underlays and overlays.